we will pick up part 4 today, which is going to be preparation for an encoded inspection, analysis and overview for flaw characterization, and we'll see some live data samples and record those, and characterization of those flaws as well for a couple different types of inspection. So once we have a calibrated sector scan or a top group or whatever we're inspecting, whether that's one group or multi-groups with multiple probes, the next step is to configure the instrument to record that data. And what separates the manual inspection from the automated or semi-automated is the encoder and the capacity of the instrument to encode A-scan and phased array data and play it back either using the instrument or offline analysis software. So encoders come in all shapes and sizes. We have examples of both extremes pictured on this slide. The simplest, cheapest form of an encoder is just a small wheel that attaches to the probe. There are string encoders that spin a wheel as well, and this allows the UT data to be associated with an X or XY position, skew, and beam position, so the data can be rebuilt in typical views such as a S-scan, B-scan, C-scan, D-scan. Those are top views, side views. The setup and configuration of the encoder is exactly the same, whether it's a small, low-cost encoder pictured on the left, or whether it's million-dollar complex mechanics with multiple axes customized for one component. The actual software setup makes no distinction between the two and can accommodate both. Our typical inspection, and what makes up the overwhelming number of inspections being performed today in phased array in general and in Olympus MX2 in particular, is the encoded one-line scan. The scan menu that we will take a look at on the MX2 shortly consists of a series of submenus of inspection, encoder, area, data, and start that we will use to convert what would normally be a manual inspection to a recorded inspection. The benefit of the phased array one-line scans on 1D linear array probes is that a traditional raster scan or a arm and wheel type movement in two directions can now be replaced with a one-line scan. That dramatically simplifies both the mechanics and the software of acquiring the data, as one access is electronic, one access is mechanical using the encoder. And these parameters are typically configured last after all of the UT and phased array has been set up and calibrated using the wizards. When we select the scan menu and the inspection submenu, we see the three types of encoded scans that are available in the MX2 OmniScan. Selecting a one-line scan limits the encoder to one encoder, and either encoder 1 or encoder 2 can be configured. The scan axis is the blue ruler, and it's typically associated with the C scan and the B scan in our software. And then based on your current configuration, the software will also calculate your maximum scanning speed. And what that means is the pulsar can pulse fast enough so that when the scanner moves, no data point is missed. If the scan were to move faster than the maximum data, you would see black lines in the data. And again, a one-line scan would use one encoder in one axis. A raster scan, like we use typically in automated corrosion mapping, would use two encoders. Typically, one would be the wheels, one would be a scan arm, or a similar configuration. also supported prior to version 4.1 is a helicoidal scan for a different type of inspection typically associated with the spiral welding. So the scanners and encoders come in all shapes and sizes. In fact, it's kind of a joke in the industry that there are no good scanners. There are only degrees of bad. And by bad, I mean the engineering it requires to stick 2 probes on a component and move them fluently and smoothly with good pressure and coupling. What seems like an easy engineering task is actually very complicated. The best scanners are ones that are designed for one particular application. And the more a scanner is adapted to accommodate multiple configurations to include TOF, phased array, multi-probe, TOF and phased array in different one-sided, two-sided, access, automated, manual, the more versatile the scanner is, the more complicated it becomes. And again, the best of the scanners are designed and set up for a single axis or one component. All of the scanners can be repositioned, reconfigured. The probes can be moved in several different positions and orientation. Some allow the wheels to be rotated, like the MX2 for parallel scanning alongside the weld. Some have chain links, like you see here, to accommodate different size pipes and a more stable probe for the phased array and TOF. Others are free-floating with magnetic wheels, like you see here. What they all have in common is an encoder. In the encoder of the MX2 that you see here, it's a simple wheel that converts a clock trigger to distance. They're typically a quadrature type encoder, and they would have a resolution that tells the software that for every number of pulses received equals 1 millimeter or 1 inch. They can be calibrated, and in general, the resolution, once determined, if there's no damage to the scanner or wear, stays very accurate. To go over what we've talked about up till now, at least for the configuration of the scan menu, we're going to transition to OmniPC to take a look at the scan axes and scan configurations in the software. So under our full menu, after we've configured the basic setup using the wizard, we've configured the UT settings for points and filters and all of the various things typical of conventional and phased array UT. We have configured our display that we want to see during the inspection, and of course calibration and all of the focal laws. So one of the things we do to convert this to a recorded inspection is first we'll set the one-line scan type as a one-line scan on an encoder. When this happens, we'll see the small icon at the top left corner of the screen change from a clock to an encoded inspection. And once that happens, the pulsar is now married to the speed of the scanner up to the maximum scan limit, which in this case was a PRF of 50 millimeters per second. The software will record every focal law or A-scan on every group at the inspection resolution entered. The configuration of the hardware for the encoder is set here. So during our inspection, we have our scan axis on encoder 2. The OmniScan MX2 has a 2 encoder input through an IP66 connector. Depending on the wiring, your one-line axis might be on encoder 1 or 2, and in this case, it's 2. So encoder 2 is configured with the polarity, which tells us which direction the scanner is moving, forward or backward, negative or positive, and it can be changed at any time. the hardware type of encoder. The overwhelming majority of them on the market now are quadrature encoders. There are several other types. The resolution in this case is 13 steps per millimeter. That means when the wheel of the encoder is moving and generating the clock trigger, every 13 triggers equates to 1 millimeter, so that the software can keep track of the scan axes and associate the S-scan data and A-scan data to the probe movement. We would normally always preset the encoder to 0 millimeters when the inspection starts. This allows us to also piece numerous welds together. If I were doing a 100-meter weld at 10-meter sections, I would be presetting file 2, 3, 4, etc. at 10 meters, 20 meters, 30 meters, etc. So whenever we talk about setting up the scan menu, we're talking about configuring the scan axes, always in blue, and it is the long axes of the B scan and C scan. So our area from the scan submenu is the start and stop position. In this case, 0 to 300 millimeters on a small test plate means that my scan is going to start at 0 when I hit the start button on the outside of the instrument, and the data will stop recording at 300 millimeters, and after we're outside of that patch, either higher than 300 here or in a negative number here, the scan position will turn red. And again, when we're inside the defined C-scan patch, the encoder position is white. When the encoder position is outside this patch, it turns red. The inspection data is being acquired at a 1 millimeter step resolution. This means that for every 1 millimeter on the scan axis, all focal laws or A scans on all groups are being collected. These two parameters, both the size of the scan and the resolution inside the scan, are directly related to file size and scanner speed. We configure the data to always record the last position, meaning that the encoder can be moved backwards and forwards and will always retain the last. And our start button is what we want to happen when I select start here or on the outside of the instrument. Moving back to our presentation. And again, that was just a brief overview of some of the types of scanners in the Olympus catalog and some of the vendors that we use as well. They all are configured exactly the same. They only differ in size, shape, and the geometry that they are designed to inspect. So that was a little bit of introduction to encoders on the one-line scan. A second type of inspection is a raster scan. Raster scan is often associated with conventional UT as it uses a two-axis scanner. When performing a raster scan in the phased array inspection, we have two axes. The scan axis, which is blue, which would typically be the wheel axis in this configuration, and the index axis, which is a green ruler that we see in this axis. So the scan axis didn't change. It's defined by a mechanical movement of the wheels and typically done at 1 millimeter resolution. But in the index axis of a raster scan, we are going to have electronic movement of the probe, and in this case, we have about a 50 millimeter total probe aperture between focal law 1 and focal law last. That combines with a mechanical movement as I spin this wheel. So I would take one acquisition 360 degrees around the pipe on the scan axis, and then I would rotate the index axes over. So this type of inspection both has to use two encoders. It must redefine how we do the area. Instead of just on the scan axis, we must define it on the scan and index axes. And it must also account for the size of the probe inside the total aperture of the phased array. That same inspection on a simpler scanner is also available by simply depressing the clicker, where the operator is manually managing the index axis, meaning that he would take one line of scan, hit the clicker, and reposition the probe accordingly for the next scan. In most of these applications, you see, using 1 millimeter pitch probes and a small A-scan aperture, we could get anywhere between about 40 and 60 millimeters of coverage on the index axis per stroke, we would call it. Index axis stroke 1, click the button, move the probe, index axis 2, and continue building the C-scan manually. Taking a quick look at that, we're going to switch to a corrosion file. We will switch the layout to the AS and C layout. I'll zoom in on an area of interest. So in this case, we have a 200 millimeter index axis, and on the scan axis, we have 900 millimeters here. So this C-scan was built with multiple strokes, we would call it, and each stroke represents a 50 millimeter line. So if we look at the scan menu, in this inspection, we've selected raster scan, and now we have to assign encoder 1 and 2 to the scan and index axes. So instead of just having one encoder, now we would have two, and they would both be configured independently with a resolution and an origin position. In a one-line scan, we only saw available the configuration for the scan axes start, end, and resolution. Now that we've switched to a two-axis inspection, also now available is the index, which again is the green side for the start, end, and index resolution. So we would build the C-scan one part at a time, one stroke at a time, continuously. The software will not allow you to configure a C-scan that exceeds the capacity of the instrument to save the data file. For most MX2s, that's 300 megabytes. For most MX2 first generation OmniScan, that was 160 megabytes. So the total number of focal laws that we're using and the inspection resolution and total size of the C-scan allows the software to determine exactly how many data points will be needed to fill it and ensure that the maximum file saving capacity isn't exceeded or allowed to be configured in a way that would exceed it, the 300 megabyte limitation. Again, raster scan and one-line scan. Raster scan, two axes, one-line scan, one axis. And again, in the raster scan now, we will also see here a scan axis and an index axis. So no matter what we do, after configuration of the UT and phase array, we configure the encoder or scanner to record the data. If we tell the software the orientation and position of the probe and configure our area and C-scan correctly, our data will accurately represent what's intended for the inspection. Things are not backwards or upside down. No matter what you're doing, if you understand the basic concepts of laying out the C-scan and configuring your probe and encoder to acquire the data, that inspection should represent what's intended. So when we hit the start button on the outside of the instrument or select the start button, the software is automatically going to preset the encoder position to what's entered here. The overwhelming majority of our inspections are single C-scan inspections, meaning they will start at 0. When we're doing a very big series of inspections and we want to piece them together offline on a computer, then we must encode them correctly. For instance, 0 to 10 meters for file 1, 10 meters to 20 meters for file 2, so on and so forth. So in the movie, you're going to see it's a very typical acquisition of about a 12-meter vessel. And this inspection is typical of windmill towers, vessel inspections. In this example, it's about a 30 millimeter thick vessel, and we're performing phased array and Toft inspection at about 50 millimeters per second, 50 to 100 millimeters per second at the maximum scan speed of the rollers. That was done using a weld rover automated scanner that doesn't require a laptop. It's just simply a handheld paddle that goes forward and backward at a fixed position. It had a laser that was walking on the weld line that allowed me to guide it while I was looking at the OmniScan periodically. Good couplant, good probe position, everything tight, all of the probe feet adjusted correctly so that we have a good gain sensitivity on both sides of the weld. All of those things are essential for good acquisition. In fact, when as a service technician working with customers, the overwhelming majority of data I see typically has more mechanical acquisition problems than software or calibration, meaning that because of the probes were not adjusted well, the mechanical carbides on the feet were not positioned well, some of the scanner mechanics may have been loose. It's obvious between different sensitivity on different groups or overall poor acquisition due to mechanical problems. Mechanical problems make up just as much problems as software or strategy problems from a technical support point of view. So moving into analysis from acquisition, the phased array analysis section, and everybody in attendance is going to receive the full version of these from the training PowerPoints. But when we talk about analysis, we're talking about 5 specific groups of information for which a accept, reject, or information decision must be made. In the 5 groups, we start with the most obvious, the amplitude analysis, linked sizing, which is very different and has a whole unique set of benefits and compromises depending on the pipe or plate, probe frequency, curved or radius, various things that we'll talk about. Depth and height sizing, which can be done similarly from manual UT as it is in the automated inspections. Volumetric position. Volumetric position means the location within the weld. It's our overwhelming first priority when making a decision. It means Volumetric position would mean, is it on the center line of the weld, or is it to one side or the other? Is it embedded in the weld, or is it connected to the outside or inside surface? Is it in the weld, or is it outside the weld in the heat affected zone? The location or volumetric position is normally our number one indicator next to A-scan characterization and two-sided detection for telling us what type of flaw it is, meaning porosity, slag. In a typical V-weld, all of the different types of failure mechanisms, lack of penetration, inadequate penetration, so on and so forth. Again, volumetric position is our key indicator. The flaw characterization is the ability to differentiate geometry from flaws and different types of flaws from each other. Different codes, different rules for cracks, lack of fusion, porosity. The ability to differentiate slag from lack of fusion is one of the big benefits of phased array and the multi-angle sector scan inspection approach. In some cases, it's very critical to the accept-rejected decision. We can have porosity and slag in most of our codes. We cannot have any cracks in any code that I'm aware of. So your ability to identify properly what type of flaw it is essential. And all of our basic analysis tools in the software, our basic analysis strategies can all be divided into these 5 groups and how we go about making a determination. Both the type of analysis required and level of precision are directly related to the setup, upfront engineering, calibration, criticality, and ultimately the cost of the inspection. So it's important to make sure that we're applying the correct strategy for the inspection. Why that's important is some of our codes require all 5 of those pieces of information to make an accept decision. But some of the codes only require 1 or 2. For instance, the AWS codes typically do not require flaw characterization, meaning they're strictly based on amplitude and length sizing. They don't necessarily differentiate between IP and a root non-fusion. You need only analyze the amplitude and the length and make a comparison based on a class defect rating system. In this case, it represents probably the easiest and least difficult type of inspection, whereas the analysis of ASME piping and pressure vessels requires all 5 pieces of information. The volumetric position reject criteria is different for an embedded flaw or for a flaw that's connected to the outside surface. To make an acceptance decision, both the depth and height and length must be known in addition to the amplitude. And of course, in these codes where cracks are not allowed, or in some cases, no lack of fusion is allowed, it's also important to draw the distinction as well. So we're going to start with group 1 of the 5 called amplitude, and obviously the amplitude is most easily arrived at from the A% reading or B% reading from the gate data. When you're doing amplitude analysis, it's important to understand what mode you are in for the gate logic. The default for weld inspection would be E here that you see, which would be peak amplitude. But depending on the application, there are other types of readings that would change how the amplitude is read. So maximum amplitude in gate A, in this case, we see 65.8%. We have a reading specifically associated with that for gate A and gate B. There are readings in the software that give us amplitude as dB above or below our reference. Even though we have a 200% signal that we can only see 0 to 100, I can arrive at the dB in relationship to my 80% reference by using one of these readings. And these come in several different variations for the various code requirements. Amplitude analysis. And of course, the color palette. On the amplitude C-scan, we see color equals amplitude, and it's designed for a typical ASME type inspection where the -3 and -6 dB drops are clear breaks in the color change. So our basic amplitude of the C-scan, which is based on the A-scan data, we can also see without any other information, just looking at this orange color, I know it's very close to 80%. I can see 40% here and 20% here. A typical ID roll, like you see here, at B0 of the S-scan, this ID roll that we see, these small indications, I can visualize those and know from the color they're approximately 5% in amplitude. And we would typically see this as a normal sensitivity for an inspection. Again, the overwhelming data we see from our technical support inquiries, customers tend to inspect at a higher amplitude than necessary because of poor or weak calibration practices. Length sizing is our next topic, and length sizing is done by the operator on the C-scan or B-scan data. The operator physically places a cursor where he visually determines the scan axis start and stop position on the C-scan and B-scan data. So the rulers associated with this, or cursors, are the scan axis reference, red, scan axis measure, and then we have a reading that shows us the delta between the two. So the operator determined the start position at 120, the stop at 155, and the delta between the two at 34.5. Our index resolution, the diameter of the pipe, the frequency of the probe, the size of the probe, all determine what type of drop method or rapid drop or -3 dB that we use. Operators tend to always oversize defects, so it's important to be conservative, and any destructive testing or upfront engineering you can do for the length sizing will dramatically improve the inspection. The ASME Section 5, which is probably the most common code we inspect for new construction, requires that the inspection be carried out at a 1 millimeter increment on the inspection resolution, meaning the blue ruler or scan axis, for materials smaller than 75 millimeters or 3 inches, and 2 millimeter increments for welds over 75 millimeters. So when we change the inspection resolution from 1 millimeter to 2 millimeters, scan speed doubles, file size doubles. So the idea is that a thicker component needs only a plus or minus 4 millimeter accuracy, whereas a thinner component, we would have a 2 millimeter accuracy on the length sizing. The smaller the diameter of the pipe, the greater the distortion, and more likely, as a percentage of the total length, the length sizing will be incorrect. For that reason, the use of curved arrays, like we use in Pipeline in the Pipe Wizard series, or like we also use in the Cobra series for small diameter piping, is very beneficial. When we are trying to identify sharply and accurately the length of a flaw, having an internal radius focus for the probe allows the C-scan and B-scan data to be much sharper and clearer in some of our small diameter pipes, even a 1 millimeter hole in the pipe will look distorted on the B scan and C scan and measure 2, 3, or 4 millimeters depending on the frequency of the probe. For that reason, it's important that our link sizing be accurate. In other words, any flaw on a small diameter pipe potentially could be distorted to look like a reject, whereas if it were accurately measured, many of them would fall within the acceptable limitations for non-fusion or for other types of flaws. So link sizing, very important. Goes directly to the reject. And we get asked often, why do we use TOF with phased array? There's generally two reasons. The overwhelming majority of our 30-degree weld bevels can be inspected without TOF. But when the weld bevel becomes more narrow at unfavorable perpendicular angles to the inspection beam, for instance, a 60-degree beam would be optimum for inspecting a 30-degree weld bevel because it creates a perpendicular inspection interface for the bevel where most flaws occur. So we supplement that with TOF. TOF aids in our link sizing, depth, and height sizing and provides a supplemental information once a flaw is determined to have meet the amplitude threshold for evaluation or reject in the phased array. TOF is also a very good complement to these instruments because it only uses a single A-scan of our 255 A-scans available, and it's a fairly low-cost conventional technique that can be added to the scanner quickly and easily. So moving on to flaw depth height sizing, we talked about amplitude and link sizing, so now we move to number 3, flaw depth and height sizing. We're going to do our depth and height sizing with cursors, just like we did the link sizing, except these cursors will be the UT axis cursors. The UT axis appears on the A scan and appears on the S scan. So we would place a cursor at the position of the bottom of the flaw, or if it were connected to the ID or OD, and we would place another cursor at the position of the top of the flaw, so that between the two cursors we're containing on the UT axis the total through wall dimension of the flaw. In a one-line scan, where the position of the probe is not available to be moved in and out from the weld, we're just seeing the weld from one fixed offset position, the ability to improve length and depth and height sizing is greatly improved by higher resolution. At a half-degree resolution, obviously, we're going to have much more information to make a determination for the height and depth of the flaw, as we would with a 1-degree resolution. In both cases, for our typical welds, they would provide 1 millimeter sizing accuracy is often a common benchmark for what people would expect paying for phased array inspections. With the use of TOF, that can be improved. The type of material, carbon steel, we would expect 1 millimeter accuracy for length and depth height sizing if we had a good plan and a good calibration strategy. The thicker the material gets, the more accurate that becomes. So in our depth and height sizing, we're going to use 2 cursors. We will also use gate data for the depth reading. So for the DA reading, it's going to take the gate information, it's going to take the max peak within the gate, and in this case, we're looking at the DB reading, which is associated with gate B, green. There's another reading, DA, associated with the red A gate. So the maximum peak within our gate, selected by our data cursor here, we see a small tip diffracted signal from the top of a crack. We'll calculate the trigonometry based on the angle to give us the depth. Okay, that's our primary reading, is the depth of the flaw, and we use the gate data in a DA or DB reading. We often use the A-scan envelope to help us peak signals. As I move the probe dynamically in manual inspection, forward and backward, or side to side, I'm watching the maximum A-scan envelope to determine where that signal peaks. Without the A-scan envelope, a dynamic reading is difficult to obtain. So get in the habit of recording your data with the A-scan envelope on. It cannot be turned on and off in analysis mode, but when recorded in the inspection data file originally, it's available in analysis mode. And it's extremely useful for calibration and peaking radiuses and peaking side drilled holes, so you get a very accurate reading. Trick techniques such as the Kraut-Kramer WSY probe and panometric CTS probe are conventional depth and height sizing crack detection probes. Those techniques are reproducible in the phase array using an L-wave wedge. In this case, we're doing depth and height analysis on a crack by scanning the probe on a clock inspection towards the flaw until it's butted up against the weld and I hit pause. The indications you see here at 70 degrees and 55 degrees are the sector scan laid out in a sound path. So we see small tip diffracted signals here that we will measure at the L-wave velocity. These two probes and any L-wave high-angled beam generates two mode-converted signals called collateral echo 1, which is a mode-converted shear wave, approximately 1/2 the value of the L wave. So this is 70 degrees. We'll see this at approximately 30. And CE2, which is what they call the creeping wave probe, which gives us positive confirmation of an ID connected crack. When CE2 is present, the crack is connected to the ID. When CE2 is not present, the crack is embedded in the material. Again, it was a conventional technique developed for the phased array equivalent that gives us a multi-angle approach to the same technique. So the volumetric position is our fourth indicator. And again, I had listed this as fourth, but in conventional manual UT, it's generally our #1 indicator to tell us what a particular flaw is, where it exists in the weld. In this example, and the weld overlay wizard allows the data to be superimposed on the position of the weld, making this a much easier function. In this example, we have embedded slag directly in the weld. It's not connected to the ID or OD, and based on its characterization and location, I can determine that is slag. Inadequate penetration in a V-weld is connected to the ID, and it's directly at the center of the weld and would be detected from both sides of the weld equally, or very high amplitude from both sides. In a OD connected crack, like we see here, we're inspecting on the second leg, shooting up into the cap of the weld, where we see a volumetric type indication with multiple jagged facets and branches of the crack. The deepest tip of that would be the through wall extent of the crack. So volumetric position, most notably from the position of the data in the weld overlay. The weld overlays are close approximations for typical scanners that don't have a band. The sector scan allows the scanner to drift a few millimeters in and out. So don't make the weld bevel precision measurement. It's just a general guideline for where the weld is at. The closer you can keep your scanner on target, the more useful the weld overlay is going to be. And we also have a reading available called the VIA reading. when the person goes out into the field to make a repair, they need to know where to dig or excavate. So we would be, in this example, the gate indication from the A-scan for this crack is -3/8 millimeters on the skew 90 side of the weld. If it were positive, it would be on this side of the weld. If it were negative, it would be on this side of the weld. And the DA reading tells us how deep. So the person repairing or trying to see the tip of this crack and excavating it would need to go all the way through a through wall dimension, but they would see the crack at 7.96 millimeters deep. If a flaw is directly on the weld center line, it would have a 0 or near 0 reading. Normally in manual UT, we consider this reading from the face of the probe, but in automated reading, we would need to measure it from the center line of the probe, a center line of the weld, because the probe is no longer available. It's on the scanner in the shop, and the flaw was marked. So our last part of this is the A-scan flaw characterization. If we look at two typical A-scans from conventional UT, we see very different indication. A planar indication, like we see here, has a smooth, flat appearance, high amplitude, a short ecodynamic travel. So we see that the rise and fall time of the A-scan is very short, meaning that it's a very sharp, clear indication typical of a calibration notch or typical of a sidewall lack of fusion or root lack of fusion, as compared to a crack, porosity, or slag, where we'll see a volumetric type A-scan with multiple jagged peaks. Okay, this is the same as in conventional UT. When we see in the S-scan data the same indications, we can see the indication from a multiple group of beams spread out between 45 and 70 degrees. So the expert was able to characterize this on an A-scan correctly, and obviously when it's inside the weld overlay and we can see the data from all of the angles in the S-scan, we can more easily and with more confidence identify this as slag. And again, it would look very similar to a crack. That fact that it is embedded in the volume of the weld where porosity typically occurs is our key indicator on top of the A-scan indication. And again here, the location directly on the weld bevel, high amplitude, short ecodynamic travel, or rise and fall time, classic indicator of sidewall lack of fusion. For these characterizations to work well and to be able to analyze with confidence, we also need to ensure that we have a good, proper calibration with TCG. Without a TCG, one part of the S-scan is going to be too high of amplitude and the other part too low. So it's very important for characterization that we equalize the amplitude. And in this case, we'll see a typical inspection report would include the maximum amplitude that we talked about, recorded on the focal law of most relevance. In this case, was used on the 61-degree focal law. We can see the depth from the DA reading of 8.68 millimeters. The volumetric position means that it is 0.76 millimeters on the positive or skew 270 side of the weld. The through wall dimension or height of the flaw is the delta between the reference and measure cursors. The length of the flaw was determined by the operator by placing a cursor at the start and a cursor at the stop on either the B scan or C scan. The flaw's location was determined to be embedded in the middle of the weld, meaning that it's not connected to B0 on the bottom on the first leg. It's not connected to T0 on the top of the second leg, so it's embedded. That has direct relevance with many of our codes for what type of table we use for an acceptance or reject decision. And the flaw type that we see based on its position, based on the characterization of the A scan, and the appearance in the data is porosity. That must be determined by the operator. The software is not sophisticated enough to be able to easily and accurately determine flaws from geometry. So at this point in the evolution of phased array and UT in general, even in the medical applications, often it's dependent on operator performing the analysis. So that is going to conclude today's lesson. We talked briefly about the encoder setup of a prepared sector scan and the 5 components of the analysis. If you have any trouble with the downloads, please email this email address and we will accommodate you using Plan B. But for those of you with FTP access, everyone will receive a follow-up email shortly after this that has all of the full presentations and a few sample data files that were used for those of you who are using software 4.0 or later. So again, we had a huge turnout for today. We see representation from most of the continents. Some people stayed up very late, and we'd like to thank everybody for participating. We have some future webinars we're very excited to be rolling out shortly, and we will see you next time. I will turn this back over to our moderator, Greg. Thank you very much for attending.
Thank you, Chris. On behalf of Olympus, I'd like to thank Chris for his participation in today's event. Thanks very much to all you, the attendees, for joining us. We hope this material was informative and useful. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event will receive a follow-up email with links to the archived presentation, as well as links to download the data files used in the presentation, as Chris just mentioned. That's going to do it for today, and again, thanks to everyone for participating. We'll see you again next time.